My name is Gwyn Edwards. I'm the director of the Common Core curriculum, and I would like to get the evening underway by inviting Professor Lung Chan, who is the convener for the Science and Scientific and Technological Literacy area of inquiry, to introduce this evening's speaker.
Thank you, Gwyn. I'm honored to introduce the Common Core distinguished speaker, Professor Richard Muller. Professor Muller, or Rich, if I may, is Professor of Physics at University of California at Berkeley, and also Faculty Senior Scientist of Lawrence Berkeley Lab. He learned physics from the late Nobel laureate Louis Alvarez, who happens to be the father of my doctorate supervisor. So for that, you know, Professor Muller is actually my academic uncle. Or in Cantonese gangster's language, 佢係我師叔. Professor Muller is a prolific scientist and a true inventor. His interest spans the fields of astronomy, physics, earth sciences, and government policies. He was a recipient of the MacArthur Foundation Fellowship, you know, which we often nickname the Genius Award. And in 1989, he was cited by Newsweek as one of the 25 top innovators of the United States. Over the years, he has authored or co-authored numerous scientific papers, including over 20 in Science and Nature. Regarding his scientific discoveries, he led the initial project to map out subtle variations in the cosmic microwave background radiation, a concept critical for the explanation of the heterogeneity and lumpiness of today's universe. He devised a supernova discovery program that led to the discovery of dark energy. And twice, his former students were awarded the Nobel Prize in Physics on a project he initiated. He also invented the accelerator mass spectrometer, which allows us to radiocarbon date a very tiny piece of material. I am particularly intrigued by his nemesis theory, which predicts the presence of a second sun in our own solar system to account for the mass extinction cycles in Earth history reported by my supervisor, Walter Alvarez. And in recent years, he has been leading a Berkeley team to re-examine the global temperature records. His work presents a stronger conclusion than that of IPCC, that virtually all the temperature rise during the past 250 years was caused by human activities. And for that work, Atlantic Magazine inducted him as one of the 21 brave thinkers, along with President Obama and Steve Jobs. And we just learned this. He is going to be named by Foreign Policy magazine in the next edition as one of the 100 global thinkers. Congratulations. And by the way, in addition to all these, he has also discovered 18 supernovas. Amid all the scientific achievements, Rich is a devoted teacher. He cares about how and what students learn. In one of his books, he writes, if you hate physics, it isn't your fault. You probably had a bad physics teacher. Some physicists intimidate outsiders by obscuring their knowledge in a fog of math. Whenever it is a little tricky to explain something, the physics teacher has an easy way out by saying, here, let me show you an equation you cannot understand. and then you won't blame my poor teaching. Doesn't that remind you of someone? His undergraduate course at Berkeley, Physics for Future Presidents, was voted by students to be the best class on campus 3 years in a row. He was bestowed the University Distinguished Teaching Award by UC Berkeley. Please join me to welcome Professor Richard Muller.
It's a pleasure to be here on being asked to talk about a subject that's dear to my heart in a forum in which we're honoring the core curriculum, which is something that I think is absolutely wonderful. It's, I think, important for us to recognize in knowledge, in productivity, in doing things, the importance of breadth of education. I studied at Columbia College in New York City, where my major wasn't even mentioned on my diploma. We were taught that breadth was important, and I really, really believe that. The other aspect of it is that no matter what any one of you does, no matter where you go, the more you know about subjects outside of your field, the more likely are you to actually make a contribution that's important and lasting. And let me give an example. When I teach my course at Berkeley, which is called Physics for Future Presidents, that's the name of the course. It used to be called Physics for Poets, but I decided I needed to have a more important goal, teach the future presidents. And when I walk into my class, by the way, before I go in, I always say to myself, what is it that 20 years from now, one of my students will be president of the US, what will I be saying? Oh, I forgot to teach him or her that. So the goal is everything is important. And I had this student who came back to me a year later. She had already graduated. And she came to my office hours. I had dinner with my mom and dad, and we had a physicist over from the Lawrence Livermore National Lab. That's where they design bombs mostly. But she had to tell me about this dinner. She said they were there, and he was working on controlled thermonuclear fusion. This is a potential energy source where the basic energy comes from the fuel called seawater, and you turn this into, and he was enthralling them, and they were sitting there politely listening, and it was fun to have a physicist there and listen to him pontificate on all this stuff. And then at the end there was silence, because what can you say? And she knew a little bit about fusion, but not as much as the expert. So she said, that's really wonderful, and I think there's real future to global, to solar power too. And he, not being so socially apt, she said, he laughed. And he said, this is a quote from her, if you want enough solar power just for the state of California, you'd have to cover the entire state with solar cells. And as she described the story to me, she said, well, I knew he was wrong. So I said to him, in 1 square kilometer, at noon, there's enough solar power coming down to generate a gigawatt. And this is as much as you get from a whole nuclear power plant. It doesn't take up much more space. And then she waited, and waited, and waited. And finally, he said, well, your numbers don't sound wrong. I'm going to have to take another look at that. Yes! This is what I want my students to do. I give them this example because this is what I want them to be able to do when they graduate, when they're president. If some science advisor comes to them and says, no, we got to go nuclear, we can't do solar, the president has to know the numbers, has to know. This was not memorizing a number. This was being able to pick out the appropriate number in context when confronted by an expert who was talking beyond his expertise. And she pegged him on it. So this is something I think all students need to study science. It used to be when you were president of the United States, all you had to know about was economics and politics and diplomacy and maybe something to do with the military. But these days, so many of our problems, maybe more than half of the things that become a presidential issue are issues that involve some level of science or technology. We can no longer afford to have presidents who don't know that material. I know actually you do quite better in this in China than we do in the United States. And so my goal is to teach the science you need to know. And what I'm going to do today is to give you an example. I'm going to give you a little mini course on science for future presidents. And rather than tell you about it, let me show you. And what I'd like, I'm going to go kind of fast, a lot faster than I would in my actual class. But what I'm going to do is to cover some important material. If I cover anything that you think is unimportant, then I've failed. So I want you to be gripped by this material, recognize it's really important. And I'll go through it quickly. When I go through it quickly, you will not be able to take notes or keep up or learn it. Don't worry about that. What I want you to do is to recognize that you have the ability to learn everything I said. We're not talking about abstracting things in some sort of form of mathematics that takes 13 years to master. We're talking about the things you need to know so you can confront a so-called expert when he gives you misinformation. So let's begin. These are the topics I will cover briefly today in the next 30 minutes. The physics of terrorism and counterterrorism. Well, some specific examples of the physics of terrorism and counterterrorism. Of nuclear power, nukes, nuclear power, nuclear bombs, energy, climate change. That's a big agenda for half an hour. Let's see how far we get. So, frightening image. Everybody recognizes it. Nobody in this room has to, that's a nuclear explosion. So let's talk about nuclear explosions. I'm going to give you the quick little mini lesson on nuclear bombs and nuclear weapons. You need to know this because there are countries out there that are developing these weapons, or maybe developing the weapons, or are they? We don't know. What's going on in Iran? What's going on in North Korea? Well, North Korea, we know, they exploded 2 nuclear weapons. Are they going to use them? What would happen if they use them? What's happening in Iran? Are they developing nuclear weapons, or are they not? I want to give you the quick education on that subject. It's going to be based on the technology, not on the politics, not on the diplomacy, but simply the technology and science you need to know to be able to think about Iran. So let's do that. There are 2 types of nuclear weapons. There are 3, actually. There's the uranium bomb, there's the plutonium bomb, and then there's the hydrogen bomb. But to set off a hydrogen bomb, what you need to have is either a uranium bomb or a plutonium bomb to trigger it. So in the beginning, you have to develop one of those. I want to be talking here about some sensitive subjects. But you need to understand these things. I want to start by talking about Hiroshima and the bomb that the United States dropped on Hiroshima, killing somewhere between 50,000 or 150,000. No need to argue over the numbers. It was horrific. Destroyed the city. That was a uranium bomb. Now, the way you make a uranium bomb is there's a certain kind of uranium, which if you have 2 pieces and they're both less than a critical mass, and you put them together, then you get a chain reaction and the thing explodes. The size of this is a few kilograms. How hard is it to do that? Well, you have to have the special kind of uranium called uranium-235. If you have the uranium-235, could you make a bomb? Did you have to have some huge Manhattan Project type team of people doing this? The answer is no. It's actually relatively easy. If you have the 2 pieces, what it takes is a gun. Anybody in the military gets access to a cannon, and you take one piece and shoot it at the other, and when it hits, it will explode. It's relatively easy to do. Why was it so difficult? Why is it so hard for countries to do this if it's so easy? If they sometimes say a high school student can do it. Well, a high school student who has access to a cannon and knows how to run it and a few other things. But yeah, it's not hard to do. So why don't more countries have it? And the answer is the uranium you get, ordinary uranium won't do. You have to have uranium-235, which is less than 1% of ordinary uranium. And separating it out is exceedingly difficult. It was done in the 1944, 45 in the United States. Lawrence, the great physicist from the University of California, created a machine he named it after the University of California. It was called the Calutron. Calutron. So he invented this thing, and it worked very slowly. You'd take the uranium and you'd vaporize it, and you'd send a beam of this thing through, and a little bit of it would stick over here, and you put a magnet there, and you could scrape off a little bit, and after a year of work, you'd have enough for one bomb. Now, 1945, after a year of work, they had enough for one bomb. Were they going to test it? No, but they didn't think they had to, because this is just two pieces of uranium-235. You shoot them together, and it'll work. Really important to know that. The uranium bomb was never tested. It was built and was dropped on the city of Hiroshima. As I said, killing 50 to 150,000 people. We still don't know exactly how many, because there was almost nothing left. So, easy to do, but hard to get the material. The calutron was a super sophisticated idea at the time. The relevance of this is that Iran is currently enriching uranium. They say, we're not designing a bomb, which is probably true. It's so easy to design a bomb. Once you have the uranium, the rest is easy. The hard part is enriching the uranium. They say they're only enriching it to 20%, even though there's some evidence they've gone up to 80%. You have to get up to 80% in order to make a bomb out of it. But 20% is the hard part. Once you get up to 20%, it's really easy using the same stuff to go those last few steps. You do that in weeks rather than in years. So basically, Iran is doing everything necessary if it wants to have a uranium nuclear bomb within a year. They're doing everything they would need. They don't have to design the bomb. This is the physics you need to know to understand what is the danger in Iran. Now, you might say, well, there's no danger in Iran. Let them have the bomb. Who cares? Hey, Pakistan has the bomb. Hey, India has the bomb. What's the big deal? That's political science, and I don't understand that. But you need to know that Iran, even though they're not designing a bomb, will essentially have a bomb within a year if they continue enriching uranium. So, by the way, Saddam was also enriching uranium, and he'd gotten up to 80%. Not enough to make a bomb yet, but he had actually done that. And some people say, wait, I thought we learned he wasn't making a bomb. And if that's what you think, you're confusing the Second Gulf War with the First Gulf War. After the Second Gulf War, it turns out he wasn't making a bomb, but after the First Gulf War, he was. And this was, what was he using to enrich the uranium? Was he using a modern method, lasers? Was he using a sophisticated diffusion plant? These are various ways of enriching uranium. It's what we do now because no, he was using a calutron. He was using a calutron. And the United Nations came in and they found his calutrons and they found his uranium and they destroyed it. He really was building a bomb, which is why so many of us thought he was the second time around. Second time around, it turns out he wasn't. But the first time around, he had a calutron. I never would have guessed he had a calutron. I mean, calutron was done in 1945. We have so much better methods then, but for your first bomb, it's not a bad way to go. That's what we did. Okay, so let's get back. North Korea took the other method. Let me go back to that. North Korea, there are two things you can use. It turns out there's several things you can use, but the two things you can use for a bomb, one of them is uranium-235, this stuff that's less than 1% of uranium and really hard to separate, because it's chemically the same as uranium. But the other is plutonium, plutonium-239. That doesn't exist in nature. It's all gone. Nothing in nature. Where do you get it? You make it in a nuclear reactor. Nuclear reactors do two things. This is something every future world leader needs to understand. Nuclear reactors are good for two things. One is they produce energy by having a chain reaction, and the other is they produce plutonium. In World War II, the United States used them to produce plutonium. They are made, when ordinary uranium has a neutron absorbed on it, we could learn all these details, they're not that hard, it turns into plutonium. Now you have plutonium. You can make a bomb out of plutonium, but not with two pieces. You can't just shoot them together. It doesn't work. It was recognized in the Manhattan Project in the United States in World War II that shooting the gun will not work for plutonium. You have to implode it, which means you have to take this plutonium and put it into a sphere and then squeeze it like a water balloon without having anything to squeeze out between your fingers. And that's extremely hard to do. You have to have an explosion that pushes it in, that's so exquisitely tuned that nothing leaks out. Very hard to do. Most of the project in the United States was in developing that explosion. Even so, they weren't sure it would work, and they tested one, and the first atomic bomb ever exploded was in Alamogordo, New Mexico, and it worked. The next one they had enough for 2 bombs. The next plutonium was exploded over the city of Nagasaki, killing 50 to 150,000 people. Horrific thing, destroyed the city. By the way, that was the last of the bombs. The US didn't have any left at that point. But that was a really top secret, that there were none left. In fact, my thesis advisor, Louis Alvarez, actually dropped a note. He was over Hiroshima at the time that the bomb was dropped, and he had a note, he dropped without telling anybody, he dropped a note down saying, we have lots of these things, and now we've shown that we're going to use them, and please surrender. I have no idea whether that note had any effect. But the note was returned to Walter Alvarez. He got it back. He has that note somewhere. Last time I asked him about it, he couldn't find it. But it got returned to him. Okay, so this is really hard. Getting the plutonium is pretty easy. You just have to have a nuclear reactor. Well, probably not too many people in this room have a nuclear reactor, although I wouldn't be completely surprised. But nonetheless, countries have nuclear reactors. North Korea has nuclear reactors. So you inspect it to make sure that they cannot separate out the plutonium that's made. And they agree to this, and they build a reactor, and we help them, and they build it. And then at one point they say, hey, you're getting too nosy. From now on, no more inspections. And they close the door. No more inspections. And then a couple of years later, they explode a nuclear bomb, which they did. Let's talk about that North Korean nuclear bomb. They're a member of the nuclear club, along with China, the US, France, England, India, Pakistan, and North Korea. North Korea now has a nuclear weapon. Suppose that North Korean bomb, the first one tested, the thing that made them join the club, suppose that one were exploded in a city. How bad would it be? Well, let's take a look. Oh, there's the Calutron again. So let's pick some city somewhere. I guess that's Hong Kong. Now let's take first as an example what would happen if one of the bombs in the US, Soviet, and I know less about the Chinese arsenals, were exploded over Hong Kong. One bomb, 1 megaton bomb. The biggest bomb ever exploded was 67 megatons. But the bombs carried by our B-52s in the United States were only 1 megaton. So what area would be destroyed by that 1 megaton bomb? That's my question. And here's the answer. Good. Okay. This is why so many of us are so afraid of nuclear weapons. That's one bomb. Or one bomb snuck in on a barge, buried under whatever comes in on those barges, and blasted off. Now let's say we took the North Korean nuclear weapon from their first test, and we exploded that at the same location. How large would the area of devastation be? It would not quite reach Kowloon or the island. Is it important to know this? Do our presidents and presidential candidates know this? Maybe they do, but they don't talk about it, because it might lead us into some mistaken sense of security. Is North Korea really a member of the nuclear club? How come their bomb was so tiny? It was tiny compared to the Nagasaki bomb, which was based on the same principle, implosion of plutonium. You need the same amount of plutonium to get the Nagasaki bomb or to get this bomb. The same amount. It's called a critical mass. You can't do it with less. This was not a bomb based on a smaller amount of plutonium because they didn't have so much. Same amount of plutonium. I believe that what happened here was that when they did the explosion, it didn't quite work and it leaked out between the fingers. And as a result, they got a fizzle. But everybody proclaims them a member of the club. I think it was a terrible disappointment. Can we stop them from developing real nuclear weapons? Well, this is pretty bad. I mean, yeah, I put it right in the harbor, but you know, hey, it would destroy the central region or whatever. It's still pretty bad. Okay, to put it in perspective, the energy released here was, we often like to express energy in terms of TNT equivalent. So a ton of TNT. That's that's what you could do if you're a terrorist and you put it in a truck and you explode a ton of TNT. The Hiroshima bomb was 13,000 tons of TNT, 13,000 truckloads. Nagasaki bomb was 18,000 truckloads. This bomb was about a kiloton, 1,000 tons of TNT. Okay, so it's pretty bad. Let me show you an event. Oh, before I do that, let me make a quick comment about nuclear power. Because many people confuse nuclear weapons with nuclear power. They believe a nuclear reactor could explode like an atomic bomb. That's like thinking that because gasoline can be used in an automobile, you can use asphalt in an automobile. A nuclear reactor, and we go into great detail of this in the course, cannot explode like an atomic bomb because it doesn't have the enriched uranium. It's designed so it can release its energy slowly, but you need that 80 or 90% enrichment in order to get a bomb to work. With that lower enrichment, what will happen is the chain reaction will go and go and go, but it goes slowly because it's unenriched. And because the chain reaction goes slowly, eventually this thing gets to the level of explosion of dynamite, and then it blows itself apart. And it stops. So you get a dynamite explosion out of uranium-235 because it's not enriched enough. And you can't get beyond that because it happens slowly. You need the enriched uranium. Again, there's one lecture on this, and you would all understand all this very well. Right now, I just have to sort of skip through it quickly. What happened at Fukushima? At Fukushima, what happened was the nuclear reactor stopped. Energy stopped being produced, but there was a huge amount of radioactivity inside that nuclear reactor which leaked out. How bad was that? This is a map showing the Fukushima region, Tokyo's here, with the red showing the places that got the radioactive exposure. Now here's something you may not know unless you read the Wall Street Journal. Probably some of you do, maybe you don't want to admit it, I don't know. But the Wall Street Journal, I wrote an article for the Wall Street Journal in which I calculated how many people are going to die from the radioactive release. A number you probably haven't heard because people don't talk about it. The tsunami, by the way, killed 15,000 people. 15,000. That's not quite a Hiroshima or Nagasaki, but it's getting up there. Huge, terrible, terrible event, killing 15,000. When you calculate the number of people who will die eventually, so far nobody's died from the radioactivity, not yet. But radioactivity does induce cancer, and when it induces cancer, they will eventually die. Many people will die. And you can calculate how many will die. If we get good cancer treatment, then none will die. But without cancer treatment, we know how many will die. Those numbers are well worked out. And again, I go into details in the course. The answer, I think, will surprise you. Fewer than 100. Largely because of the evacuation. This is a really terrible nuclear accident, but because they evacuated, now they can move back in. The radioactivity is way down. The number will be less than 100. I'd love to give you a lecture just on that. Okay. What about nuclear waste storage? Isn't that a big problem? Again, it's a greatly exaggerated problem. These are calculations that show the drop in radioactivity of the nuclear waste as a function of years. And after 1 year, 10 years, 100 years, after 100 years, I plot this a little bit differently. I plot this as a function compared to the radioactivity that was taken out of the ground when the uranium was removed. You mine uranium from the ground. It's radioactive material. It's in the ground. And so when you take it out to make a nuclear reactor, you're reducing the radioactivity. When you make this nuclear reactor after 100 years, it's 100 times greater than the uranium you took out. 100 times greater, but only 100 times greater. Is that hard to store? It's a lot safer than a lot of poisons that we store. If 10% were to leak out, and had a 10% chance of leaking out, then that's back to where we started in terms of danger. So the nuclear waste, when you know the numbers, so what's going on in the United States? What's going on in the United States is that President Obama promised the senator from Nevada that he would close the site if he got the support of the senator from Nevada. And when the senator from Nevada supported him, he closed the site. I wouldn't be saying that here in China if I didn't say that every time I speak in the United States. And I'm on videotape, and you can find me saying that. It's a terrible thing that was done, just for political advantage. Okay, let's move on. Let me talk about a well-known terrorist attack that released more energy than the first North Korean nuke. This is well-known. You've heard of this event. I believe you have all heard of this event. And it released more energy than the North Korean nuke. And it was a terrorist event that killed people. You know what I'm talking about? Don't shout out. It's a rhetorical question. I'll remind you of it with the following photo. The energy in the jet fuel of that airplane was greater than the energy in the North Korean nuke. Astonishing. How can that be? Well, the reason is, here we have a list of objects and the energy compared to TNT in this column. And you notice TNT comes in at 1. Actually, that's, yeah, TNT. But if you look at gasoline or jet fuel, it's the same. 15 times more energy per pound than TNT. How could that be? Why do we use TNT then? And the answer is because it releases this energy very rapidly. Rapid release of energy, like a hammer. You put energy into a hammer slowly, but then you get it out rapidly. And that's a force multiplier. It means what you put a force here, a few pounds of force, so that it may weigh a pound. You put a few pounds of force on it, but when it hits, you may get 500 pounds of force, because that same energy that was put in over a meter swing is released in a millimeter. And so you get 1,000 times force multiplier. That's what a hammer does. It's a force multiplier. It doesn't give you more energy than you had. It multiplies the force. So we use TNT because it releases the energy much more rapidly than gasoline, even though it's 15 times less energy than the same amount of gasoline. If you want to destroy a car, and you're given 1 pound of material to do it, you might pick 1 pound of TNT. You're actually probably better off picking 1 pound of chocolate chip cookies, giving them to some high school students, and giving them sledgehammers. So this energy is completely out of whack in the way we think about it. Now, what happened to the World Trade Center? There was basically there was about 400 tons of gasoline in each plane, and multiply that by 15, and you get energy release that's much more than a kiloton. Of course, it wasn't an explosion, and when you see when the explosion happened, most of that jet fuel didn't explode. Most of it was still there, slowly burning. Well, let me just show you what happened, how the building collapsed. Why did it collapse? I'll do a little bit of architecture here and engineering. You all know that paper is pretty strong when you pull on it, but if you put any weight on it, it has no strength at all. So that's common knowledge. Why am I doing this? Well, can I do anything more boring than show you that paper has no strength? Well, suppose I were to take the paper and now roll it up, put a piece of tape on it. We just take that same flimsy paper and roll it up like that, and make it into a cylinder, a remarkable thing happens. Paper has no strength. Amazing. This is the sort of thing that got people like me to become a physics major. When you're a kid, you see something like that and you say, how can that be? And yet it's not surprising, really, when you think about it. By the way, this is a principle that every architect, every engineer has to really understand, because you're not going to use a chunk of steel to hold up a book if you can use a piece of paper. Now, of course, there's a danger that this looks kind of flimsy. So let's put in a safety factor, make it a factor of 2 safer. So when you build this thing, you have a factor of 2, and that's in fact the way the buildings are built. They're built with materials, but the walls that support things, the columns that support things, have a factor of 2 safety factor. They can hold up twice the weight they have to hold up. Now, an interesting thing happens when you heat steel. Heat means the molecules, which are always bouncing around a little bit, bounce faster. That's what heat is. It's the bouncing of molecules. They don't move typically, except in a liquid or a gas. But in a solid, they stay in the same place, but they're vibrating. You heat them up, they vibrate more. When they vibrate more, they tend to bounce harder and they move a little bit further apart. That's why when you heat things, they expand. Now, they move a little bit further apart, the forces are weaker, so they're not quite as strong. And so, for example, if you heat up steel, not to softening, not to melting, but just heat it up to 600 degrees Celsius. You could easily get that with your stove. Get a lot hotter than that with a gas stove. But just heat it up to 600 degrees Celsius. Then, because the vibrations are faster, they're moving further apart, the forces are weaker, the steel will lose half of its strength. Half of its strength. That means it won't hold up the book anymore. The best way to attack a building is to heat it up with a fire. Not try to explode it. Just heat it up with a fire until it loses half of its strength. And that's like doubling the weight. And then it collapses. But when it collapses, it doesn't collapse. It collapses catastrophically because you have buckling. And when you have something that you're squeezing like this and begins to go, suddenly you're no longer that cylinder. Suddenly you're now this, and there's no strength at all. And it seems to fall at free fall. And I've seen so many articles written by someone saying, anybody who knew any physics whatsoever would know that that building could not have been collapsed in this way. It came at free fall. It must have been a detonation. Oh, explosives put in there. So it's ridiculous stuff from physics. Rosemary, my wife is here. She remembers on 9/11 asking about how the building exploded, and I explained it to her. I went to my class the next day and said, I'm going to change the lecture. For one, I said, yesterday there was this terrible event. Let me tell you what happened. And I told them about this and how it works and so on. Also about metal detectors and how the terrorists had pulled it off. It was pretty obvious to anybody who knew a little bit of science and technology. You didn't have to understand it in depth. You didn't have to solve differential equations. All you had to know is know a little bit about materials and how they weaken. And you would understand all this. And this is something everybody can do. And you don't have to be a scientist or a physicist to understand this. But you need to understand it if you're going to evaluate various threats. And what potential threats are there? Well, let's see, I pointed out here the difference between TNT and gasoline is a factor of 15. So an attack by gasoline, in my mind, is a much, much greater terrorist threat than an attack from a nuclear explosion. Because the terrorists can't get the uranium-235, and if they use plutonium, it probably will fizzle. And why should they do that when all they have to do is take an airplane and run it into a building? It's hard to run airplanes into buildings these days, and so I don't expect a terrorist attack to occur in any country that is somewhat careful about this. Yeah, the Homeland Security rules at airports are a bit overdone. I know the things I would abolish, but they're very good at keeping it from happening again. Back in 2001, I told my class it's not going to happen again, not in the next decade. It hasn't. Now, is there a danger? No, I still don't think there's a danger. It's not going to happen again. Again, I can talk about that. Okay. We're on energy per gram. And now I'm comparing gasoline to batteries. This is important. This is something every future world leader, every future financial leader, whether you're a president of a country or the president of a company, you need to know these things. I've told lots of potential investors about this. Look at the energy difference between gasoline and an expensive rechargeable computer battery. It's a factor of 100. Gasoline has 100 times the energy per pound of a battery. Now, battery is electricity, and you can use that more efficiently. You can make an electric motor, which works better than a gasoline motor. So if you want to make an electric car, you don't have a factor of 100 disadvantage, probably only a factor of 30. Why don't we have electric cars? Or why do we have electric cars, but only electric cars that the wealthy can afford? Most famous electric car in the US is the Tesla Roadster. People don't appreciate that it has 1,100 pounds, forgive me for the American units here, but 800 kilograms of lithium-ion batteries. So it's 2.2, it's about 500 kilograms of lithium-ion batteries, which, by the way, cost 40,000 US dollars, 400,000 Hong Kong dollars. Huge expense. And the trouble is the batteries don't last. So after driving, after you've recharged them 500 times, you have to replace them. And so now you can calculate what will it cost to replace the batteries. And I put down the number here. It's 3.4 Hong Kong dollars per kilometer driven. The gasoline costs you 1.6. Electricity costs you almost nothing. The cost of an electric automobile is not the cost of the electricity. It's the cost of replacing the batteries. We can get around this, and we can get batteries that can be recharged 2,000 times instead of 500. And 6 or 7 years ago, there was a company called A123 in the US that claimed they could do this. And I watched their progress, and there didn't seem to be any. And in my recent book, which I haven't mentioned, this is the book that collapses, my Energy for Future Presidents book, that there was no progress in A123. It wasn't getting cheaper. And then just last week, they declared bankruptcy finally. So, I mean, electric car will work if you're willing to put up with a range of 100 kilometers. Because then you can use inexpensive lead-acid batteries. And those can be recharged many times. They don't cost that much. So if in the United States, people won't buy a car like that. But there are many places in the world, in India, for example, which people would be delighted to have a 100-kilometer range. And that's where the electric cars would work, but not these expensive ones. They have to be the cheap batteries. Hubbert's law is something a lot of people know. The United States oil production started dropping in the 1970s. We basically produced what we had. And when oil is first discovered, people then keep on looking more, and the amount goes up, and then you run out and it goes back down. That's called Hubbert's law. What I'd like to do is summarize for you what the situation with the fossil fuels in some major countries around the world. This is something where you can just look up the numbers, and yes, you can look them up, but that doesn't mean that you know them when you need them if you're the president of the US or China. So let me run through some of the numbers, and I think you will find some real surprises here. So I'm going to use numbers that are just official US numbers. I'm not going to change them. I would change them if I wanted, but let me keep my own prejudices out of this. They're not all exactly correct, but let's assume they are. These are US numbers, and they're pretty close. So each one of these is a different country. I haven't told you which. And this is the amount of recoverable oil they have underground. My challenge to you is guess which country is which. Can you locate Saudi Arabia? Can you locate Venezuela? Can you locate China? Can you locate the United States? Can you locate Australia? Okay, so let me put the labels on. And now that you've had your mental exercise of trying to guess which is which. And here's the United States, and here's China, We have very little. And the king of oil is Saudi Arabia. And next comes Venezuela. And next comes Canada. Canada? Yeah, it's Canada. Why? Because once the price of oil shot up above 60 US dollars per barrel, then the huge reserves that were considered unrecoverable can now be recovered. These are oil sands, and they're very expensive to get the oil out. And nobody ever imagined. Back 10 years ago, the chief scientist of BP came and he gave a lecture. I still have his lecture notes. And they knew about this stuff, but they said, well, of course, that's impossible because it had to be $60 a barrel. The price will never go up that way. I mean, right now, they would say it was $20 a barrel. It'll never go up to 60, but it has. And today, it actually dropped down, I think, to $86 a barrel. So Canada reserves are really high unless the price drops. And investors are worried that the price will drop. And if the price drops, this is what will happen. So the reserves depend critically on the price of oil. But the oil is so expensive that all sorts of things are becoming possible. Now, okay. Let me now tell you about something which is so new and so dramatic and so important that you will be embarrassed if you don't already know about it. I assume most of you will be embarrassed. This is a revolution in energy, in fossil energy. And some of you already now are guessing what I'm talking about, but some of you have no idea. A development of the past 15 years in fossil fuel energy. I'm going to now add on to this the resources that these countries have in natural gas. And these numbers are very different from the way they were 15 years ago. Enormously different. And I'm going to put them on in the same units, billion barrels of oil equivalent. So that's energy units. And here we go. You might be particularly interested in the United States and China. And look at those huge reserves. Our two countries, are relatively poor in oil. We have huge reserves of natural gas that we didn't even realize could be extracted as recently as 15 years ago. Enormous reserves. These are called shale gas. Some of you will be hearing that term for the first time. But when you start looking at the newspapers, you'll see it's all over the newspapers, and you just hadn't noticed it. And it's extracted by a method known as fracking, which is a shortcut for hydraulic fracturing. And there's a great deal of opposition against fracturing because when done badly, it can be environmentally bad. The way it works, so anyway, hey, we're on a par with Saudi Arabia. Not quite the same, but on a par. The way it works is that you drill down, curve the drill into the narrow shale layer. You never would have imagined you could do this. It's only 20 meters thick. And then you set off explosive shaped charges that crack this. And then you pump down water and sand to expand the cracks and the sand to prop them open. And then you extract the water and the gas comes out. And this is absolutely astonishing. Let me show you what's happened in the United States for this technology, which, as I said 15 years ago, was just beginning to be appreciated. But this is the increase. This was 2005. That's only 7 years ago. And there's very little, but look what's happened in the United States. It's shot up. I'm going to argue that we need to have a similar shoot up in China. We'll come to that near the end in the policy stuff. That we need to do this. By we, I mean not just you, but I mean the world. We need to have you develop the natural gas. You'll see why. Let's go back to that same plot that I had before. And there it is. Well, I've squished it a little bit. Okay, it's the same number, same plot. I just put the numbers down. And that's because now I'm going to add in another fossil fuel, coal. There's the US. Hey, China, Russia, enormous reserves of coal. What's important about coal? The thing is you could turn it into gasoline. And by the way, think for a moment, which country in the world is the most advanced in the technology of converting coal and natural gas into gasoline? Which country in the world is developing plants that can do this more rapidly than any other country in the world? The answer is China. Okay, so what's the bad news? The bad news is all this stuff produces carbon dioxide, and carbon dioxide produces global warming. So the good news is energy security. We're not going to run out of fossil fuels. The bad news is it produces global warming, and coal produces a huge amount of local pollution. You can clean it up, but it's very expensive to put all the scrubbers in the stacks, as in China, I believe, understands this better than anywhere else. Okay, let's talk about climate change. 3 years ago, I was actually here visiting Hong Kong University, talking about my plans to do a global warming study. On Monday, I gave a talk in which I went in detail on what we did. Let me just show you the results. I'm really proud of this. This is a plot of temperature versus time over the world, going back to 1753. And what do we see in this plot? We see cool periods when there are huge explosive volcanic eruptions that get into the upper atmosphere and reflect sunlight. So we get these huge explosive volcanic eruptions. And each one of them is a dip in temperature that only lasts about 3 years. And you'll notice for the geologists here, there's some mystery. Why were there such these big explosive volcanic eruptions here, and now there are only little puny ones like Pinatubo and Krakatoa? Anyway, that's an interesting scientific question. But the smooth curve, what is that? The smooth curve is a plot of the carbon dioxide influence. And the fact that it fits the data so well took me from being a skeptic into someone who said, wow, as far back as the late 1700s, the human production of carbon dioxide was already beginning to change. We had thought that much of this could have been due to the variability of the sun. The sunspots were coming and going. But when we look at this, there is no signature for sunspots. The fingerprint of sunspots is completely gone. And so this is our result from the study that we've now spent 3 years doing. What I'd like to do is to show you a little more detail, a movie, let's see if we can get this running, which is from our work. And what it will do is show you the variability in location. See, we only measured the land. And what I showed you before was the average, but now you can see things coming and going. You can see cool periods and hot periods. Notice how it bounces. It's quite violent. And what's going on here? Why is it? It was just red there in Europe for a moment, as red as 3 degrees Celsius more than the average. And then it's blue, and then it's red. It's bouncing around. This kind of behavior comes about mostly because of variability in the weather and in the flow of ocean currents. We're getting up to 1861, and we have pretty good world coverage now. Antarctica is the last continent to come in. But look at that bouncing around. Look how it pulses. Real big heat waves. In 1880, was that big heat wave probably enough to kill people in the local region in Siberia. When these heat waves come and go, should we blame them on global warming? Over here on this scale, you can see how much global warming there has been. This little bouncing red dot shows you the warming, and it's warmed up a little bit by maybe 1 degree Celsius. But these heat waves are much bigger than that. People will claim every time they see a heat wave as global warming. 24, watch the United States in 1933. So Western United States, you'll see, boom, that was the Dust Bowl. Read Steinbeck's novels, you read about the Dust Bowl. It was a localized event, it wasn't happening in Europe. Now, the scale is beginning to climb up. It was fairly level here, around 1980 it begins to climb up. And this part is what the UN organization, the so-called IPCC, attributed to humans. And it will start climbing up, bouncing around, but the bounce is the average. You see the local bounces are much, much bigger than that. And here it comes up. And around 1998, 2000, you'll see everything gets pretty red. We chose the color scheme, of course, so that in 1998 it would get pretty red. But here we go, there it is. Now everything is pretty warm. And we're in global warming. So that's global warming. That's the result of our study. You can download this movie from our website, which is listed up there, www.berkeleyearth.org. So look up Berkeley Earth, one word, spell Berkeley right. By the way, what has it been like in Hong Kong in this period? I pulled up the plot for Hong Kong. And what you can see is the warming from around 1950 till now has been half a degree, half as much as the world on average. You haven't gotten your share of global warming. Not only that, but the red line curve is actually a 5-year running average. If you look in the last 5 years, so it doesn't have a red curve, you see it's dropped back down to where it was in the 1950s. So if you think you could experience global warming by walking outside, the temperature is the same as in the 1950s. People love to say you can tell global warming, but you can't. You can if you have hundreds or thousands of measurements. In the United States, there are little fluctuations like that. I made a plot of the United States. The red curves, the red crosses are all the places where the temperature over the last 100 years has gone up. The blue ones is where the temperature has actually gone down over the last 100 years. There are twice as many red as blue. That's global warming. But if you happen to live in a blue, you might be a climate skeptic. The problem is there's so many things. Everybody wants to say, oh, something bad happened. We had a hurricane. We had a typhoon. It must be global warming. Beware. Most of that is simply looking for something dramatic so they can convince you that global warming, the melting of, well, the IPCC said that the Himalayas might melt by 2035, and they were wrong. Well, let me not dwell on all this right now. The number of hurricanes is, I don't have the data for the typhoons, but the number of hurricanes has actually been going down with time. The number of tornadoes has been going down with time. But you cannot attribute higher variability to global warming because the variability has been going down. More storms, no, the number of storms is going down. I gave a lecture on this subject on Monday, and I don't have time to go into it. Remember, I'm only trying to give you a sample. Now, here comes the real shocker. And if you didn't know this, you might ask yourself, why not? These are the carbon dioxide emissions coming up from the United States and China over the past, I don't know, 15 years or so. 1970, last 40 years. Emissions of carbon dioxide by the US and China. 2006, China surpassed the US. China continues to grow. Last year, according to the official Chinese report, 9.7% more coal was burned than the previous year. It's growing at about 10% a year. The US is going down. If we project this, it depends on whether the Chinese economy continues to grow. Let's assume the emissions grow not at 10% per year, but only 6% per year. Assume that's also true of the rest of the developing world. And here we have the emissions of the emerging economies. And meanwhile, if we had signed the Kyoto Treaty, which we didn't, the US would be going down. I'm sorry, Kyoto we did sign, we just didn't ratify. This is the Copenhagen Treaty. It would be going down. It's going down anyway. Why is it going down? The amazing answer is that the United States is now at its lowest emissions of the last 20 years. The lowest emissions in 20 years. And virtually all of that decrease is coming because we're switching from coal to natural gas. Now, coal is basically carbon. You burn carbon, you get CO2. Natural gas is mostly methane. Methane is C with 4 H's. You burn that, and the H's burn to make water. And that's okay, no problem. And you burn the carbon. You wind up for methane and carbon, you get, for the same energy, you need 3 of these, which means 3 times the carbon dioxide. So for global warming, the most, well, let's say not the most, but there are 2 really important things you can do if you're worried about emissions of carbon dioxide. One of the 2 really big ones is to switch from coal to natural gas. If you can do it, if you have it, if you have the resources. Well, you saw that China has the resources. They're not all in the best possible places. You'd love to have them around the coastal cities, maybe right over here and so on, but they're not there. And so there are technological problems. But I am arguing to the US government, to everybody I know in Washington, that if we want to reduce carbon dioxide. Far more important than solar cells in the United States. Far more important than electric automobiles. Far more important is to help the developing world develop their resources of natural gas, enabling countries who don't have the fracking technology, and right now it's almost all in the United States, to enable them to use the fracking technology to switch from coal to natural gas. By the way, the other thing you can do is use your energy more efficiently, and we're talking about that too. I don't have time to talk about energy efficiency and energy conservation, but it is huge. That has to be done. Now, you're probably familiar with this. This is a map of pollution. This is particulate pollution in China. According to the World Health Organization, if it is white, it's okay. You've probably seen the satellite photos. That's smog. That's a bad day. We've been blessed, in our stay here in Hong Kong. It's just been wonderful weather. Thank you for arranging that, however you do that. So this is familiar to most of you. So in the end, and here I'm going to finish up. On the issue of global warming, on the policy issue, global warming so far is real but small. Most of the things attributed to global warming are nonsense. If you know people who are skeptics, they're probably right on more things than you, because they probably believe that the storms are not due to global warming, and well, the storms are going down actually, and so on. So have respect for the skeptics. Many of the skeptics are simply people who look at the data more carefully. But nonetheless, global warming is real, and it's going to go up. And the reason it's going to go up is because we are using more fossil fuels. And by the way, a simple switch to electric automobiles, if you get that electricity from coal, you're going to produce more carbon dioxide than if you made it out of gasoline. That's because coal is so much worse than even gasoline. Okay, so climate change is exaggerated, but it could be big in the future, will be big in the future. I'm expecting that within the lifetimes of most of the people in this room, global warming will make a warmer climate than has ever been experienced by Homo sapiens. Not there yet, but we're getting very close. Measures to stop it: think global, act global. This thing, think global, act local, I don't think works. You got to act global. Act global means a worldwide switch from coal to natural gas and energy conservation. And those are the two answers. So that's my mini course. And yes, there is nothing in this lecture that is either unimportant or not within the grasp of the point where you could argue the case in front of someone who didn't know it. So that you should aspire to do that. This is important material, technological material, but really important for the major issues of the world today. And I'll end with that. Thank you very much.
Well, thank you, Professor Muller. Now, I believe some of you will eventually become the chief executive of Hong Kong or the prime minister of China. But I urge you, you should know some science, and you can do so without much equations. Okay. Now at this point, could we open up to the floor for questions? If any among the audience have questions for Professor Muller, please raise your hand, and we have some microphones going around.
Thanks, Professor. Really, the point about natural gas is very interesting, but I was wondering if there are other implications on switching to natural gas from coal.
Okay, there are several important issues there. One of them is that natural gas has been produced in the United States in a way that has not been good for the environment. And because of that, there's a powerful movement to stop it. That movement is not just in the United States. France has outlawed natural gas. The fracking technology has have others. The two issues are, one, local pollution from dumping the water into the ground, the wastewater that comes up. And my answer to that is easy. If anybody does that again, you just make a fine that'll put them in jail and make them lose all their profit. That's easy to handle. One thing we know how to do is clean up water. We can do that. It's just a matter of enforcing it, and we haven't yet. The other is that some of the natural gas might actually leak into the atmosphere. And it's a worse greenhouse gas than carbon dioxide by far if that happens. So we have to monitor these stations and make sure that they don't leak. Again, I've been looking into the technology of this, and that technology is a little bit hard, but it's so much easier than developing cheap rechargeable batteries or putting in the infrastructure for wind power or cheap solar cells or all of these other things. So in terms of a technological challenge, clean natural gas is not hard. I refer to it as clean fracking. So fracking in the past has been dirty, largely because it's been rushed and competitive, and there have been no regulations. And now we simply have to put those regulations and enforce them vigorously, and then it can be done more cleanly than almost anything else.
Thank you. Maybe over there, the testing. Does it work?
It's right
Sound, yes.
More on the question of fracking. Recently, it has been covered, and a lot of people have been asking questions about the possibility of fracking causing localized earthquakes and a lot of other unknown consequences due to it being such a new technology. And I remember also reading about the use of heavy metals in the underground. Mm-hmm. Do you have something to say on that?
Yeah, on both of those topics. The first one are small earthquakes. They have been detected. They're magnitude 1 earthquakes, which means if you're standing right above them, you cannot sense them, but they can be sensed by seismogram. Nonetheless, this makes worries. I think the best answer to that is that the fracking technology is not actually that new. It has been used for coal bed methane in the past, just had not been used. And so there's really a lot of experience on this. Now, the Swiss recently shut down a test they were doing. It turns out it wasn't for fracking natural gas. It was for extracting heat energy out of the ground. And they pumped water in, and there were some earthquakes. They decided not to do it anymore. And that one, I looked at that, and it seemed so exaggerated compared to what I knew fracking could do. I finally realized, oh, the reason they're canceling that is because it was a bad idea in the first place. The energy from the Earth coming up is 3,000 times stronger than the energy of the sun coming down. And I'm averaging a night for the sun, too. 3,000 times difference. So anybody who's trying to extract geothermal energy, unless it's at a place where there's a volcano or a geyser, it's going to be a project that's going to lose money and go out of business. And so they made an excuse. They canceled it because they said there were earthquakes. The fact is the earthquakes are all very small. You recognize we're talking about something which is several kilometers underground. You're fracturing something which is 10 meters in size, and you're fracturing it very little. It's hard to imagine you'd get a big earthquake out of this. And in fact, there never have been.
Now, I know many of you are starving, but please stay with us for a few more minutes so that we can properly honor this distinguished lecture.
Actually, any of you who are starving, please leave, and I'll be happy to talk to the people. I will not be offended at all. I understand you have lots of important things to do. You're welcome to go, really.
Wear them first.
I just got a question. It's a very interesting presentation. And my question is that at the end of your slides, you say...
Oh, there you are. Okay.
Yeah, sorry about that. I should have to wait to you earlier. So at the end of your slides, you mentioned the future of climate change lies in the hands of developing countries like China.
Yes.
But from a different perspective, countries like China, they have to consume more energy so that they can develop economies so that people can have a better life.
That's right.
So it seems like a developing economy and controlling climate change are conflicting objectives for countries like China. So do you see a way out for China?
Absolutely, absolutely. No, I want to see China grow. I think it's wonderful to see the developing countries develop and deliver all the wonders of good, the things you can afford, right? Not good food, good health care, good opportunity, good education, all the things. Those are the sine qua non, those are the things we all want. But you don't have to get your energy out of coal. You can get it. One of the things I'm really proud of China for doing, unlike the United States, is pushing nuclear power. nuclear power is also clean. And the US, because we're somewhat paranoid about it, mostly because of activist groups who don't understand the physics, we start suppressing nuclear power. And then Japan says, well, we're going to go back to nuclear after this terrible thing. Oh, only 100 deaths. Well, even so. Why should we do it if the US doesn't? And we can say, oh, but China, they're smart. They're doing nuclear power. So you want to go nuclear? You want to go to natural gas? The reason you're going to go to natural gas instead of solar? Because it's cheaper. And there's only one thing that's cheaper than natural gas, and that's energy conservation. Getting the same standard of living, the same quality of life, by using 1/3 of the energy or 1/4 of the energy is eminently possible in almost every location. And people don't do it. And they don't do it because they think they have to invest too much. But in terms of investment, it's the best investment you can make. So I believe the answer is to use technologies in the developing world which are profitable. Natural gas and energy conservation are highly profitable, and therefore it makes sense to do it. It's more profitable. I mean, you know, the U.S. could try to sell the technology to China. I think we should give it to China, and because it's a worldwide issue, and we can help you make a profit while reducing carbon dioxide emissions.
Okay, let's try to squeeze in a few more questions. Who has the mic? Oh, over there, William.
Hello. I think I should make my question short and quick. So in the current culture, how should we impose or require political candidates to have the scientific knowledge, especially nowadays in the general culture of Hong Kong, for example? Most focus on education is to learn something practical rather than to learn physics or science in general. So how can we enforce that?
Yeah, well, enforcing who becomes a candidate is an issue way beyond my ability to know. Certainly, I think what we do need to do is to make sure that the public asks the right issues. I'll give an example of the current presidential debates, 3 presidential debates, 1 vice presidential debate, lasting 4.5 hours total. Some of you may know the number of minutes spent discussing global warming in those 4.5 hours. 0. The issue wasn't raised. Now, I think part of the reason the issue wasn't raised is because it's no longer in the hands of the US, and neither president wants to say, well, what we should do is share our technology with China. That's the quickest way to, we got to get them elected first and then have them say that. I mean, there are political issues here that I don't claim to understand, but I bet that one is one where they could get into trouble. But 0 minutes in 4.5 hours? 4 years ago, this was a big issue. And George Bush, he was this real idiot on climate change, and Barack Obama was going to save us all. And now it's not mentioned?
Does that mean they will be elected with no science knowledge?
Well, I think to get people elected with science knowledge, we need to, I mean, the long, slow way is to get the public knowledgeable on these subjects. That may be the only way that really works. At least get the newspaper reporters knowledgeable on these subjects. And I can tell you some stories about newspaper reporters. But we have to get this more into the dialogue. We have to get people to talk about these issues.
Okay. Maybe Daniel first, and then I know you are anxious to get a question in, right? Maybe Daniel, you'll do it.
Yeah. Hi, sorry, just to change the subject slightly. Can you share with us a little bit how you designed your curriculum, please? Sorry.
Oh, yeah. Actually, I've written about that. The curriculum was basically designed to start with the most exciting subjects first. So do nukes right at the beginning. Every subject, you begin with the application, not with the basic physics. By the time in the lecture on radioactivity, within 5 minutes, I'm talking about radioactivity and cancer. And then after an hour of that, everybody wants to know the difference between an alpha ray and a beta ray and a gamma ray. But if you start with alpha, beta, gammas, you're not interested. Anyway, I can send you an article I wrote on the curriculum development. But I actually have a textbook for this course. Not the popular book, but the textbook that has 12 chapters on 12 key issues. And it's unlike any curriculum I've ever seen. So I can't give you any more in 30 seconds. But I'll be happy to tell you much more about it.
Okay, your question first, behind you.
Hello. Here. Thank you so much for your lecture. It's really appreciated. I have one question that I don't agree with your gas part. Because right now you suggested that there's a 10% growth rate of gas production. So let's say if we ask developing countries to develop their gas resources, so that could be increased to 14%. That means within 5 years, the production of gas is going to double. That means within 10 years, it's going to give a 4-fold increase. So what's after 10? Because we don't have enough gas. So what's after 10 and 15 years? Because if there's an exponential growth rate.
Oh, can we show the slide again? What I'm going to show you is that in the United States, the gas rate, this is now 30% of our natural gas. And it just started in 2006. This isn't a doubling in 5 years.
If the rate is 14%, then it will double in 5 years.
Let me get you the right one here. I have to find the right slide. Excuse me. Yep. The old Microsoft PowerPoint was so easy to find the right slides. And now that they have improved it, there it is. Okay, so this was the US in 2006. And this is us 7 years later. That's not doubling. Now it's 30% of our natural gas.
Right.
So it's only 30%.
But if the growth rate is
But the result is our emissions have been going down while our energy use has been going up. So yeah, the numbers are important, and you're absolutely right. And you have to work out these numbers. But energy conservation, in principle, could be done instantly. Not really. You have to put insulation in your walls. You have to have more efficient motors. There are a long list of things you can do. But there's nothing else that's in the ballpark. Nothing else that's big enough. Nothing else that really offers hope. So yeah, this will take 10 years to get really going. But at this point, I would say, look, global warming hasn't been so bad. Sea level, you know how far it's gone up? It's gone up by 20 centimeters in the last 100 years. 20 centimeters in 100 years. We're not about to be flooded by the sea coming in, which is an impression you would get if you watch An Inconvenient Truth. And if you look really carefully, you'll see that Al Gore in Inconvenient Truth was talking about 1,000 years from now when he was flooding New York City. It didn't look like the New York City would look 1,000 years from now. But the projection came from a UK scientist. He wasn't endorsing it. He was just passing on some scary stories that were based on continued growth of carbon dioxide over 1,000 years. We're not going to have fossil fuels for 1,000 years. So these scare stories were really good in the United States for getting people into action. And then after a few years, they learned that they were tricked. And I think that's another reason why this subject isn't being brought up, because Nobel Prize winner Al Gore wasn't really telling you the truth, inconvenient or any other way. Polar bears are not dying because of receding ice.
May we take one last question? How about over there?
Thank you. I'd like to ask, what's your view on the future of electricity car? Because nowadays the battery used for the car is really expensive. Do you think are there any disruptive technology will emerge soon, which will make electricity car really, really popular? Thank you.
Okay. On the electric car, I have been really working with some of the advanced people working on electricity. And what's happening with these batteries is they are getting improvements, but they're happening incrementally. It's not like we have seen in the computer, which was exponential. It's not like we've seen on hard drives, which was exponential, and even despite that, they're going away. It's going up slowly. And the reason is there really are no new battery technologies. We know the chemistry. You can get the battery handbook, and it's all there. There are really no new things coming along. What we're trying to do is get the recharges up. Now, recharging a battery is really tricky because you have chemicals that diffuse across the electrolyte, and they deposit themselves over here. When you recharge it, you send them back. They better go back to the same place. They tend to build dendrites, little fibers that grow and grow and grow and short out the batteries. And as a result, getting it to recharge more than 500 times is really hard. There's certain chemistries the sodium sulfur chemistry, for example, they can get thousands of recharges. Now they're trying to get that with these other with lithium ion. Lithium ion is just going to be too expensive. It's never going to go. So the answer on electric cars, the electric cars being developed in the United States, no. By the way, I get more hate mail on electric cars than on anything else. However, if you're willing to accept the limited range that you can get from a lead acid battery, then it's competitive with gasoline. So if you're willing to go no more than 100 kilometers before you have to recharge overnight, then yes, then there is a future for electric cars.
Okay, thank you. I'm sorry, I apologize. There are a lot more hands than the time could allow for. And with this, I'd like to conclude this distinguished lecture. And please join me to thank Professor Rich Muller again.
Thank you very much. Just two things to complete the evening. First of all, to remind you that tomorrow evening at 5:30 there will be an opportunity for you to continue the conversation with Professor Muller, and seeing the number of hands that were up who were unable to ask questions, I'm sure that there will be a very, very good turnout. So the event will take place in room 112, the first floor of the Knowles building. So 5:30 tomorrow, and let's hope we can continue some of the kind of controversial and interesting discussions that we began to generate here. Finally, could I invite Professor Amy Choi, who is the Pro-Vice Chancellor for Teaching and Learning, to present a souvenir as an appreciation, a token of our appreciation.
Have a common core as the
Okay.
Thank you very much.
Thank you.
Thank you.